Hello, this is Dr. Sudhansh Sharma from School of Computers and Information Sciences. I welcome you all to this session. And this session is about discrete mathematics. In fact, this is a course MCS 212, and it is a very comprehensive course and has very many components and which are exclusively requiring understanding of mathematics. And the core objective of today's session is to let you understand that what is the role of mathematics in computer science. This is an introductory session, but the tidbits of various components will be discussed in this session. So far as MCS 212, that is discrete mathematics, is concerned, this is first lecture in the series, and this lecture is comprised of the discussion about the predicate and the proposition logic. Apart from that, we will be discussing about the concept of the Boolean algebra. Whereas this course of MCS 212 has got various components. Likewise, we are having set theory, relations in functions. We are having probability theory, counting principles, likewise permutation and combinations. We are also having the theory of automata and Turing machines. Apart from this, we are also discussing about recurrence relations and graph theory. So this is a very comprehensive course, but you need not to worry. We are going to have a series of lectures, and you will be able to understand the concepts in an easy manner. Now, the first and the foremost thing, the objective of today's session is to let you understand that why we need mathematics, what is the role of mathematics, and apart from discrete mathematics, do we have some other kind of mathematics? If there is some other kind of mathematics, in which kind of application does that mathematics is applicable? Whereas the discrete mathematics is a distinguished component of computer science, and it has got a different sort of role in computer science. In order to begin with, firstly we should understand that what for the computers are required. Actually, nowadays n number of applications are there. Likewise, we are day in and day out listening about artificial intelligence, machine learning, chat GPT, likewise generative pre-transformer models, large language models, generative AI, data analytics, data science, name any field, be it image processing, signal processing, networking, or anything. Mathematics comes into the picture. So one has to understand the concept of mathematics because it plays a role of an interface in between the real world and the computer world. Whenever we are going to design any application, we are supposed to take into consideration that what are the requirements of the real world. So considering the requirements, analyzing the requirements of the real world, we design some solution. And in order to design that solution, the modeling of the design or the modeling of the analyzed components is required. Thereafter, the engineering is also performed, maybe about the optimization and all those things. And in that case, the role of mathematics, statistics, operational research, all these things comes into the picture. Thereafter, whatever the outcome is there, that outcome is tried to be implemented in the form of software, maybe in some programming language. And apart from this, hardware implementations are there. Nowadays we are having sensor networks, we are having IoT applications. So hardwares and softwares goes hand in and hand out. But the thing is that in order to implement all those things, you are supposed to have the understanding of the mathematics in order to formulate the real world requirements. So this is for what the discrete mathematics comes into the picture. Now I request to show the slides first. So this is your discrete mathematics 1, and the main objective is the outline is that why do computer science students need mathematics? So we need to understand the influence of mathematics on computer science. Generally, the students of the computer science feels that we are supposed to learn about the implementation part. We are supposed to go for the programming. Why should we study mathematics? What is the role of mathematics? Why should we study for set theory or relations and functions? But they are the backbones of any application. Now, since computer science is discrete in nature, we are having different type of mathematics. So we are having discrete mathematics and a continuous mathematics part. So and computer science is discrete in nature, so we will be talking about the discrete mathematics. Apart from this, how discrete mathematics is actually the backbone, is actually contributing to different areas of computer science that is required to be understood, and we will be learning all those things in this session. Now, computer applications related to mathematics are, we will be citing some examples, but you will see and you will find that in your everyday life you are coming across with n number of applications wherein the computer science, wherein the mathematics is playing the vital role. Now, answer to the first question is that why do computer science students need to study the mathematics? Now, actually, what for the computers? The first question is that prior to computers, do we have computers? I don't think. कंप्यूटर से पहले हमारे पास कंप्यूटर्स नहीं थे तो क्या था? कंप्यूटर से पहले हमारे पास we were having basic sciences, physics, chemistry, mathematics, electronics, electrical, and all these fundamental sciences actually joined the hand together to build up the computers. But what for the computers are required? Actually, the intellectual strength in the society was quite less, and in order to impart intelligence to the machines, the intellectual persons thought that in order to have a homogeneity in the decision making, why should not we replicate our intellect and we should pass on our intelligence into the machine? So because the intellectual persons, the wise persons cannot be omnipresent, they cannot be available everywhere to solve the solutions, to provide the solutions. And hence it was required that they devise some machines wherein for the benefit of the society, that the people can use those machines to take some decisions and to come to some conclusions. So the ultimate goal was actually to impart the intelligence. That's why nowadays we are talking about the concepts like artificial intelligence, machine learning, deep learning, and we are nowadays moving towards the concept of the machine wisdom, because decisions can be made by the machines, decisions can be made by the human beings, but are those decisions wise enough? Are those decisions optimum enough? Are those decisions good enough that they can be implemented in the right manner for the benefit of the society? So for the implementation of the intelligence into the machine, likewise for the solution of any problem, there are different phases. The phases involves analysis, design, and implementation. So analysis of the problem is required, and then to find out the design so that the problem which is analyzed, which is identified, whatever gap analysis is performed is to be formulated, and that formulated problem is to be designed so that it is well understandable. And once the design is well understandable, we are supposed to go for that, the mathematical modeling, we are supposed to go for the simulation part. And because now the problem is very well understandable, we can implement that problem in any programming language. So again, we are saying that computer science in any language, likewise we are having Java, we are having C, C++, Python. There are also languages, likewise we are having Hindi, English, Spanish, or any other language, because the language is the component which is having some grammar, some alphabets, some strings, which can be concatenated all together. So one of the very important role of discrete mathematics is nowadays into the natural language processing, wherein we are able to process the components of human languages, and we can translate them, we can transform them into signals, into text into voice, voice into text, or whatever we want to do. So all these things are implementable because we need to have a common platform. Whatever real world requirement is there, in order to transform that into the computer world, we need to have an interface. We need to have a common platform, and that common platform is actually provided by mathematics. And what kind of mathematics? That is discrete mathematics. So we also learned that prior to computer science, we were not having anything like computer. So different sciences and mathematics plays the vital role in formulating the computer science. So in many departments, we are having computer science as part of the mathematics department, and electrical and electrical engineering department, and computer science department. So computer science is an applied science. It is the application of the fundamental understanding. The domain understanding is very much required. So we would like to understand that what kind of mathematics are there. There are two types of mathematics: discrete and continuous. So can you please show the slides? So in order to understand that what kind of mathematics is discrete and what kind of mathematics is continuous, so let's take an example of a digital watch and an analog watch. In a digital watch, whatever time is coming, whatever time is shown, likewise 310 or 125, so that is very discretely identifiable. But in an analog watch, likewise a watch which is having needles, okay, there is a hours needle, there is a minutes needle, there is a seconds needle. So there is a continuous progression. Say the time in between the time interval, say T1 to 1:25 p.m. to T2 1:26 p.m. there are infinitely many possibilities of the occurrence of the times in the milliseconds, nanoseconds, and microseconds, or whatever. So there are n number of possibilities. So that means the possibility of occurrence in between the two time intervals is infinite. So such distribution, such type of data is continuous, and in order to deal that type of continuous part, continuous distribution, we need to deal with a different type of mathematics, wherein we are generally supposed to deal with the integral calculus, differential calculus, differential equations, and although these mathematical components also comes into the picture when we are going to study the machine learning part, because we are going to replicate that into the human intelligence part. And there's a different, we are having linear algebra, we are having different components of mathematics, wherein we also deal with the continuous data. But in the discrete data, whatever occurrence is happening is clearly identifiable. Likewise, if we are tossing the coins, the heads and tails, they are clearly identifiable outcomes. If we are tossing a dice, the outcomes 1, 2, 3, 4, 5, 6, they are clearly identifiable. So whatever things are clearly identifiable, so that means the integer occurrence of the data is actually reflecting the discreteness of the data, whereas the real number representation is actually reflecting the continuous types of the data. But computer science is primarily meant for decision making, whether to take the decision and or not to take the decision. That means whether yes or no, true or false, 1 or 0, success or failure. So discreteness is there, clearly identifiable components are there, nothing in between the two. So such type of components are taken care in the field of discrete mathematics. So computer science is discrete in nature because we are supposed to impart intelligence. They are supposed to use computers for decision making, and decisions are binary in nature. So what do we mean by discrete mathematics? That is, discrete mathematics deals with a separated or discrete set of objects rather than the continuous sets. I hope you are able to understand what is the difference between the discrete and the continuous sets. And it also processes with a sequence of the individual steps. Likewise, I had discussed that when we are some experiments are there, say we are tossing a coin, or say we are tossing a dice, or we are distributing the cards. So clearly identifiable events are there, random variables are there, and there is no possibility of occurrence of any event in between the occurrence of two events. Likewise, in the case of a digital watch, 125 means 125, 126 means 126. The least count of the watch is say minutes only. So we are neglecting any occurrence of the seconds in between the two time intervals. But when we are talking about say analog watch, then n number of possibilities are there in between two time intervals. So such type of data is your continuous data, and in that case we are supposed to deal with the continuous distribution. So if we are going to discuss about the statistics and mathematics part, let's focus about the discrete mathematics part. We are having different elements of discrete mathematics, and the same are incorporated into our course of MCS 212, and we are having as discussed earlier also, we are having set theory, relations and functions. Why I'm using relational again? Because relational algebra we are having in relational database management system. For query optimization we are using relational algebra and relational calculus, and we are having relational database management systems. So that's why we are having relations and functions in discrete mathematics. So hope you are correlating, able to understand that relations and functions are playing dominant role, vital role in relational database management systems. Those who had studied relational database management systems in their bachelor's or in their school system, they might have recalled that in relational database systems we are having functional dependencies. There is a question why we are not having functional databases, why we are having relational databases. Why not we are having relational dependencies? Why we are having functional dependencies in relational databases? So understanding of set theory, relations and functions, if you are not able to understand these concepts, your roots in the field of RDBMS will be quite weak. So in order to strengthen that, you should have the understanding of the mathematical concepts clearly taught in the subject and of discrete mathematics, and set theory, relations, functions, probability, permutation, combination, graph theory, recurrence relations, and automata theory. They are all in distinguished component of discrete mathematics. Pick any of the book available in your library or available on the internet. You will find that these are the indistinguished components, and they are very well explained in the literature, in the self-learning material available for MCS 212. So I hope till this part of the session you are able to understand that why we are supposed to study discrete mathematics. So there are some examples, some type of questions which are generally asked, that how many ways can we connect the computers when we are configuring a LAN, or say longitudes and latitudes if are available. We human beings have crafted the maps. God has never, भगवान ने हमारे को कोई नक्शा बना के नहीं दिया. It is a human being who had drafted and crafted the maps. So how the maps are drafted, how the maps are produced. So man has partitioned entire earth using longitudes and latitudes. We are having equators and prime meridians, and using that knowledge of longitudes and latitudes, we are devising the concept of the GPS, and we are using GPS day in and day out for positioning any mobile, for positioning any car, any vehicle, for on map, for positioning any instance happening on the earth. So that is, we are using mathematics in the form say again the mathematical model which is coming over here is your matrices. So longitudes and latitudes, the data available produces a matrix, and matrix can be transformed into the respective data structure, say arrays or linked list, and which can be implemented in any other formal programming language. Now we are having the concept of the probability, and the probability concept is very much used in the field of machine learning. We are having naive Bayes classifiers, wherein the Bayes theorem is prominently used for classification purpose, and classification is actually the labeled approach. What do we mean by the labeled approach? And let's understand this. Say we are trying to find that some car, say we are trying to find, say some car model, say Maruti or any brand. So brand A. So we are having the picture of that brand A. Now whatever cars are passing through the road or on the highway, we are going to map that whether this brand is passing or not. So we are having a label of that brand, and within an hour how many cars of that brand are passed, so we can identify that which is the most promising brand in that region. So we are classifying that what is the percentage of cars of that particular brand in that particular region. So we are classifying it, although in that case we are using the approach of supervised learning, and we are using naive Bayes classifiers for classification. How we do that, we cannot discuss it right now, but surely the concept of probability, conditional probability applies over here, wherein we can use the classification. Therein afterwards we are having the concept of clustering, which is a unsupervised approach, and we again apply k-means algorithm. Different algorithms are available wherein the mathematics plays the vital role for the identification. Apart from this, for network theory, we are use Dijkstra's algorithms. We for spanning tree identification, we are having Kruskal algorithms, Prim's algorithm. These all algorithms are very much covered in your course. So please show the slides. Now we are having different applications and some are listed over here, and we will be discussing in this session that we are having digital electronics, wherein we are using the concept of Boolean algebra. We are having networking, wherein we are using the concept of graph theory. Relational algebra, we are using the concept of set theory, relations and functions. Apart from this, we are in the concept of the data structures. We are using counting principles, permutations and combinations, because we need to find that which loop run how many times in order to find the time complexity and the space complexity of any algorithm. Apart from this, artificial intelligence is there, where we are exploring predicate and the propositional logic. No doubt set theory also plays vital role over here, and we will be in this session we will be discussing about the predicate and the propositional logic, and we will be also discussing about a bit of the Boolean algebra. Therein we are having cryptography, again encryption, decryption schemes are also involving mathematical tools. There are n number of applications. Many applications are also discussed. Likewise, GPS systems are there, digital image processing, because again image is also a matrix of pixels. Pixels are picture elements, and we are using the concept of the matrices when we are trying to produce some effects on the pictures. Likewise, we are trying to change the color, contrast, intensity, brightness, or we are trying to fuse one picture into another picture. Then we are doing all type of matrix operation. We are multiplying the matrix, we are adding the matrices, we are doing a number of matrix operation when we are dealing with the digital images. So mathematics plays a very important role. Now let's begin our session with the concept of the digital electronics. Now because in the beginning we said that what for the computers are required. The computers were devised to take the decision, to impart the human intelligence into the machines. So computers are comprised of both hardware and the software components. The hardware designs involves memories, involves control signals and many more components, but whatever components we are talking about all involves gates. So gates, so those who have studied electronics, electrical, and maybe from the science side had studied science in 11th and 12th will be aware of that we are primarily having fundamental gates and OR and NOT, and we are having the universal gate NAND and NOR. But designing of these gates is primarily dependent upon the Boolean algebra. The concepts which we are going to explore for Boolean algebra are also applicable in the field of predicate and the propositional logic. So AND gate, OR gate and NOT gate, and we are also having the XOR exclusive OR gate, are in the propositional logic are actually the replica of conjunction and disjunction. Now conjunction actually replicates the AND logic and disjunction that means replicates the OR logic. Now what do we mean by AND logic? AND logic means whatever inputs are available to any logic, all the inputs must be high to have high output. And OR logic says that if any of the input is high, then output is high. And exclusive OR, that is XOR logic, states that if any of the input is high, then output is high. Now please focus on this table. We are having inputs X and Y. Since two inputs are there, so how many possibilities there? There should be 4 possibilities. 0, 0, 0, 1, 1, 0 and 1, 1. Now say let's start with the OR logic, that is the disjunction logic. In the context of the discrete mathematics, we name the OR logic as disjunction, and it states that if any of the input is high, then output is high. Now X and Y both are low, that is 0, 0. So that's why X or Y or X disjunction Y is 0. Now X is in the second entry, we are having X is 0 and Y is 1. So if any of the input is high, because Y is high, Y is 1. So X or Y or S disjunction Y in this case will be 1. Now again focus, next entry is 1, 0. Now 1 is high, Y is low. If any of the input is high, then output is high. So in third row, X or Y, we are having 1. Now final entry, both X and Y are 1. Since both are high, so output should be high. So X or Y, X disjunction Y will be 1. Now let's understand how AND logic or conjunction logic works. Now conjunction logic says that if any of the input is high, if all the inputs must be high to have high output. So conjunction logic says that all the inputs must be high to have high output. Now let's understand it row wise. In the first case, we are having X and Y 0, 0. Since both are 0, none of the input is high, none of the input is 1. So X and Y or X conjunction Y is 0. Now X, Y, second row, X is 0, Y is 1. So X conjunction Y, that is X and Y, if what is the definition of conjunction? All the input must be high. Since one of the input is low, so output will be 0. Again in the third row, X is 1, Y is 0, so X conjunction Y will be 0. And the final row 1, 1, because both are high, so if all the input must be high to have high output, therefore the final row under X and Y, X conjunction Y will be 1. Similarly, on the same lines of action, we will be having XOR, and XOR, the statement of XOR, that is exclusive OR, is that all the input must be high to have any of the input odd numbers of input must be high to have high output. If any one of the input is high, then output is high. So in this case, we are having X 0 in the second row, 0 and 1. X is 0, Y is 1. So that's why X XOR Y is 1. Secondly, in the third row, X is 1, Y is 0. So odd number of inputs are high. So that's why output is high. If any one of the input is high, then output. What for the XOR is required? XOR is required when we are going to go for the parity checking, sign bit checking, whether the number is positive or negative. So if any of the input, that means odd numbers of inputs should be high, then we are having high output. So this is the difference. What for these conjunction, disjunction, exclusive OR are required are to represent the logic. And you should understand that in order to represent the logic, the De Morgan's law plays a very vital role. Those who had studied digital electronics will understand that we are having A and B is equal to A or B, and the same equivalent of De Morgan's law in propositional logic in terms of discrete mathematics is not of A conjunction B is equal to not of A disjunction not of B. Similarly, A or B is equal to A and B is equal to not of A disjunction B, not of A disjunction B is equal to not of A conjunction not of B. What for De Morgan's law required? De Morgan's law are generally required when we are going for operator transformability. In the very beginning, we learned that we are having different type of gates. The fundamental gates are there. We are having, please show me. We are having AND gate, OR gate and NOT gate. And we are having the universal gates, that is NAND and NOR. So how to derive AND or NOT, that is fundamental gates from the universal gates? This is possible by using the De Morgan's law. We exclusively use De Morgan's law when we want to derive fundamental gates from the universal gates. That is, when we want to develop AND gate from NAND gate, or OR gate from NAND gate, NOT gate from NAND gate. But from the practical point of view, what is the requirement? So let me give you an example. If we are developing any electronic circuit, now in electronic circuit we are supposed to use ICs. Now if we are developing the circuit with the help of the fundamental gates, then we need to have three type of ICs, one for the AND gate, one for the OR gate, one for the NOT gate. But if we are using the NAND gate, then by using single IC for NAND gate, we can devise both all three, that is NAND gate, or AND gate, OR gate and NOT gate, simply by using that single IC of NAND gate. Similarly for NOR gate, by using single IC, please show me. When we are using the NOR gate, by using the single IC, we can develop all three type of gates, AND, OR and NOT. So that means the cost effectiveness of the circuit is improved. Instead of using three ICs, now we are using single IC. Apart from this, when we are using the wiring part, the flow, the circuitry is involving enormous number of wiring when we are using three types of ICs. But when we are using single IC, the performance of the circuit also improves. So De Morgan's law are used for operator transformability when we want to transform conjunction into disjunction, or AND into OR into AND, that is disjunction into conjunction. And this is very much required when we are planning to derive universal gates from the fundamental gates. Now you should understand that mathematical modeling is done prior to the implementation part. Why I had given you this example? Because when we are implementing the gates through, say, semiconductors, we are implementing the gates. But in order to implement them, prior to that, we are supposed to go for the mathematical modeling. And when we are going for the mathematical modeling, we are using the concept of conjunction and disjunction. So by listening to the term, one should be able to understand that in which domain we are working. When we are using the term conjunction and disjunction, that means we are into the mathematical domain. We are talking about the discrete mathematics component or we are working with the Boolean algebra section of discrete mathematics. But when we are using the concept of conjunction and disjunction, that means we are using and or. We are using and or as a terminology. That means we are into the implementation phase. We are into the digital electronics. So Boolean algebra is actually the mathematical firm footing for digital electronics. When we are designing the circuits, we are using Carnot's map, and when we are using Carnot's map, we are actually applying sum of products principle and product of sum, and those concepts are actually implemented in the form of conjunctive normal form and disjunctive normal form in discrete mathematics. So mathematical modeling is to be done prior to the implementation part. Generally people think that the researchers goes in the way that they do analysis, design and then implementation, and that is the right track. And generally people think that we need to implement, and whatever we implement then we are supposed to map in the backward manner, and because of that n number of problems happens, and many a times softwares collapse because they are not, their requirement, their functionality are not analyzed in proper manner, their functionalities are not designed in proper manners, henceforth the implementation is not proper. So in order to implement the things, you are supposed to understand the mathematical concepts behind the implementation. Now please show the slide. Now over here some circuitries are shown to let you understand. On the right side we are having the tables. One table is representing the discrete mathematical equivalent, that is the conjunction, disjunction and exclusive OR part for any proposition. The tables in the middle are actually the replica of the discrete mathematics equivalent in the digital electronics format, and the circuits in the leftmost section are actually representing the working of AND, OR and exclusive OR gate. So in the AND gate you are finding now, if you focus on this, now this is the situation when both are 0. After now it is 0 1, now 0 0 is there. So you can find that when 1 1 is there, output is 1. AND gate is the light of AND gate LED is on. Similarly for OR gate, if any of the input is connected, or if both the inputs are connected, then light of LED is on. And similarly in the exclusive OR gate, if any of the inputs is conducting, then only the output, that means the exclusive OR gate LED is turning on. So just focus on the LED. When LED is turning on, the on section of the LED is actually representing that when the output is turning out to be 1. When the LED is off, that means the output is 0. So you can directly map that from the circuit we are mapping with the digital electronic table, which is right in the very middle, and in the very right side we are having the discrete mathematical equivalent of your digital electronics table in the format of conjunction, disjunction and exclusive OR part. I hope it is clear to you. Now you need to understand that behind digital electronics, again we need to have the understanding of the propositions. Propositions actually are the logical sentences whose output can be either true or false. What is the application? Why should we study predicate and the propositional logic? What is the difference between proposition and predicate? When to apply proposition logic? When to apply predicate logic? We need to understand this. Now the next question which might be occurring in your mind, that why should we study this? What is the relevance? Where it is applicable? Nowadays in natural language processing, we need to transform human sentences into computer understandable format and computer sentences into human understandable format, and various languages are available. We are watching the TVs, we are watching the movies, and the movies can be translated from one language to another language in runtime. So what is happening at the background? So as I already said, analysis, design and implementation. You are just seeing the implementation phase. What is happening at the background? We are actually playing with the language models, wherein at some point predicate and the prepositional logic also plays a vital role. So because languages need to be the predicates and the proposition. Proposition is some statement, logical statement which can whose output is either true or false, and predicate is a generalized statement, whereas proposition is a specialized statement. We are talking about, say, person particular, but when we are giving generalized remarks, then we are not talking about person particular. So how to deal with such type of statements? So we need to have the understanding of generalized components, wherein we are supposed to explore the concepts of the quantifiers. In propositional logic, we are having the concept of the operators, that is conjunction, disjunction and negation. But apart from conjunction, disjunction and negation, so far as predicate logic is concerned, we are supposed to explore with the concepts of existential quantifiers and the universal quantifiers. Nonetheless, in both the concepts, we are having the concept of the implications and double implications. Now, as I already said, that conjunction is mathematical equivalent of AND operation. AND operation is all the inputs must be high to have high output. So generalization of proposition is predicate. So predicate is a generalized statement. So operators, that is conjunction, disjunction, negation, are very much available in propositions. So when we are generalizing, so generalization of operators leads to quantifiers. So if I say conjunction, the generalization of conjunction is universal quantifier and generalization of disjunction is existential quantifier. Say I cite an example कि ये चीज जो है सभी के लिए है, this is for you and you and you and you and you, that is for all. So that means generalization of conjunction is for all operator, for all quantifier. And if I say this thing is for you or you or you or you, any one of you, so that means generalization of disjunction is existential quantifier. So that means we are having operators in propositional logic and we are having operators and quantifiers both in predicate logic. On the same line of action, we should understand that when we are having De Morgan's law for operators in propositional logic, so and we are having generalization of operators in predicate logic, so we should have De Morgan's law for predicate logic also. So what was the De Morgan's law for proposition logic? Negation of A conjunction B is equal to negation of A disjunction negation of B. Negation of A disjunction B is equal to negation of A conjunction negation of B. In the terms of discrete digital electronics, not A and B is equal to not A or not B, not A or B is equal to not A and not B. So we will be discussing about how these laws are being generalized in predicate logic. But prior to that, let's understand what are propositions. Please show the slides. So propositions logic is the area of logic that deals with the proposition. And what are propositions? A formal mathematical language for precise reasoning. So we are supposed to construct multiple, say, complex propositions. In order to let you understand, let me cite you some examples. A proposition is a declarative sentence, a sentence that declares a fact and is either true or false, but not both. So let's discuss what are propositions and what are not propositions. So Delhi is the capital of India. So this is, yes, this is true. Read this carefully. No, you cannot say it is true or false or what. So this is not a proposition. So 1 plus 2 is equal to 3, that is correct. And x plus 1 is equal to 2. You don't know anything about x. What is x? So you cannot say anything, you cannot take any decision. So this is not proposition. So what time it is? So it is not a proposition because it is not specifying the time. If it says that it is 3:45, then okay, at this point of time it is true. So you need to understand that propositions are logical statements which are either true or false. They cannot be altogether. So we are having, in order to understand the proposition logic, please show the slides. We are having some, we need to understand something. That proposition logic is a logic which deals with the propositions, and propositions are statements which can either be true or false. So we actually are applying the symbolic logic over here. We represent the proposition with the help of the variables. Say variables, generally we take P, Q, R, S, and it is up to you, whatever alphabet you want to choose, you can choose any of the alphabet as a variable. And say we can cite a proposition that today is Friday. So today is Friday is proposition or not? Yes, it is a proposition because today is Friday. And the output, the true values can be, the truth values can be, or the outcomes can be true or false. And as I already said that these are the tools for the reasoning, and in order to form the valid reasoning part, we need to construct valid sentences, and in order to construct the sentences we use the operators: conjunction, disjunction, negation. We use implication, double implication. Likewise over here, but you need to understand that there is some precedence of using these operators, and the precedence is shown over here, and based on the precedences we need to parenthesize the propositions, and these precedences are actually helpful when we are solving the expression. Actually, these precedence rules plays vital role. Likewise, when we are solving the problems in mathematics, likewise we apply BODMAS rule. So bracket, open, divide, and then multiply, and then add, and then subtract. So there is some precedence. So it is not like that first we subtract and then we multiply or then we add. So some precedence is specified, and based on that precedence the rules are to be applied, and then only we can lead to some correct conclusion. So precedence rules are to be followed. So in order to formulate the conditional statements, we need to have the understanding of the implications and double implications. So let's understand what are the conditional statements, and what is the meaning of premise or fact or antecedent, and what do we mean by conclusion, and how the logic of implication actually works. So in order to understand that, let's study that. Let P and Q be the proposition, then the conditional statement P implies Q is actually meaning in English that if P is there, then Q is there. If P is true, then Q is true. If P is false, then Q is false. In the conditional statement P implies Q, P is called the hypothesis or antecedent or premise, that is, it is a fact. And based on the fact we are supposed to derive some conclusion, and Q is called the conclusion or the consequence. So in order to understand the concept of P implies Q, a conditional statement, say we take an example, if I am selected then efforts are high. So P is selected and efforts are high is Q. So let's understand it in the format of, say, a truth table. If a person is selected, then obviously the person might have put high efforts, so that means the outcome is true. So in the first row you are having selected comma high effort. The first T is for selected, the second T is for high effort, and thereafter the third T is for the conclusion, that is the result is true. If the person is not selected, so that means false. If the and the second is high effort is true. If the person has actually placed the high effort, then the person is not selected, that is false. Definitely he should be selected, and that is true. You will understand when we are going to apply more and more examples, because these things are related with the point of reasoning. Now, if the person is not selected, and that means no higher efforts are being placed, so this is also true. So that's why we are having false, false, and true. That means the person is not selected. If the person not placed the good efforts, then person will not be selected. But if no higher efforts is false, that means the person has placed the higher efforts, then not selected will be false. That means the person should be selected. This is again true. Now in the final row, the selected, no higher efforts. That means if the person has not placed any higher efforts and the person is selected, that is not possible. Be it anyways, the person has to place some higher efforts. So implication is actually replying. We are having some other concepts. Likewise, converse is there. The converse rule says that if P implies Q, then Q also implies P. Contrapositive rule says that if P implies Q, then not of Q implies not of P. That means अगर P है तो Q है, पर Q है ही नहीं तो P भी नहीं है. और कन्वर्स का मतलब है P कहता है Q है, और Q अगर है तो इसका मतलब P भी है. Similarly, inverse of P implies Q. That means P है तो Q है, पर P नहीं है तो Q भी नहीं है. You will be using these things in order to identify whenever we are using these rules. We are say many times we are supposed to understand whether the statement is valid or invalid, it is a tautology or a contradiction or a fallacy, whether the statement is satisfiable or not. So these terms are very much vague. So in order to this is generally for the qualitative study. So in order to quantify the qualitative aspects, we need to have some laws for reasoning. And implication and double implication are playing vital role in reasoning. I just repeat again that discrete mathematics plays the vital role in imparting intelligence to the machine. And intelligence requires reasoning. And in order to do reasoning, you need to have the understanding of the implications. Rules of implications. What do we mean by contrapositive? What do we mean by inverse? What do we mean by converse? What do we mean by syllogism, hypothetical syllogism? And we are having n number of rules, modus ponens, modus tollens. All these rules are covered in the course. And now we are supposed to let's understand through an example that many times in the question papers and in the examinations, people are asking that transform this English sentence into its mathematical equivalent, or transform this mathematical expression into the English sentence. So you need to be very much conversant with the topics of the proposition logic, wherein say over here, let P be a statement, Maria learns discrete mathematics, and the Q statement, Maria will find a good job. So expression statement is P implies Q as an English statement. So the solution is that if Maria learns, so if P implies Q, if Maria learns discrete mathematics, she will find a good job. Or Maria will find a good job when she learns discrete mathematics. Or for Maria to get a good job, it is sufficient for her to learn discrete mathematics. That means discrete mathematics and your job are interrelated. So this is to let you understand what do we mean by implication, but greater details are available in the self-learning materials also. Now we are also supposed to understand the concept of logical equivalence, wherein we are supposed to understand the concept of double implication. That means P implies Q, then Q implies P. So the logical equivalence of proposition, let P and Q be the proposition, then by conditional statement P double implies Q is the proposition. P if and only if Q is there, That means the biconditional statement P double implies Q is true when P and Q have the same truth value and is false otherwise. So P double implies Q has the truth values as P implies Q and Q implies P, or conjunction Q implies P. Now conjunction is both the inputs must be high to have high output. That means P implies Q should also be true and Q implies P should also be true. Then only the result will be true. So in the English sentence you will be saying if and only if. So if P double implies Q happens in the mathematical format, then its equivalent English statement will be I double F. That means if and only if. So the example is, let P, you can take the flight, and Q, let Q be, you buy a ticket. Then P double implies Q is a statement, you can take the flight if and only if you buy a ticket. So implication is if you buy a ticket, you can take the flight. So both are interrelated, that if one statement is true, if both statements are true, then only the outcome will be true. So this is related when we are going to understand about the logical equivalence of two statements. Now we can understand this concept with the help of the truth table also. Please show the slides. We are having P double implication as tautology. Now tautology is the concept wherein all the outputs are true, and contradiction is the statement wherein all the outputs are false. So the compound proposition P and Q are called logically equivalent if P double implies Q is a tautology. Why we are saying P double implies Q is a tautology? Because in the earlier slide we learned that P implies Q, conjunction Q implies P, and conjunction means and means all the input must be high to have high output. So that means P implies Q should also be true and Q implies P should also be true. That means the outcome should be tautology, all should be true, then only the output will be true, and this leads to the logical equivalence, which is represented by the notation P now equal to, as there are three horizontal signs you might be seeing over here, denotes that P and Q are logically equivalent. Now in the truth table you can see that if we decompose implication by using the operators, then we can see that P implies Q is actually replica of not P or Q. And if we populate this truth table, we are finding the outcomes under the column not P and Q or Q. That means not P disjunction Q is actually mapping with P implies Q. So that means P implies Q and not P disjunction Q are logically equivalent. So let's try to understand one more example, that how to translate an English sentence into its mathematical equivalent. Earlier we learned how to translate a mathematical equivalent into English sentence. Now we are trying to understand translating English sentence into mathematical equivalent. So say directly come to an example that you cannot ride the roller coaster if you are under 4 feet tall unless you are older than 16-year-old. Now to translate this English expression is having three symbols, three type of requirements. You can ride the roller coaster, say it be Q. You are under 4 feet tall, say it represented by R, and you are older than 16-year-old, say it be represented by symbol S, variable S. Now the sentence can be translated into R and not S. That is, you are under 8 feet tall and you are not older than 16-year-old. This implies Q negate of Q, that this implies you cannot ride the roller coaster. So that means by using the symbolic logic, we are able to generate a compound proposition. I hope you are able to understand by this moment that what do we mean by predicates, proposition, what is the role of discrete mathematics in digital electronics, how mathematics and computers are interrelated. You will be able to understand all other details in our subsequent lectures, and you will find that this subject is quite exciting and promising and will provide you firm footing in the field of computer science. I would like to end this session for today. Thank you.